reason is that it satisfies a couple of conditions. Okay, it has a couple of properties. For example, what is the property number one? Property number one is that there is a notion of constituents. Okay, so I can say the table consists of molecules. All right, so they are constituents. Okay, fine. Now, what does it mean to have constituents? Constituents means that there is some, in case of table, there is a counterpart, okay, which I can describe as an asymptotic state, for example, asymptotic state of an S matrix. This is a molecule or atom or whatever you want to call it, right? Now, this molecule I can describe as asymptotic state, okay, and the table, or whatever my macroscopic object, is made out of this, and it's legitimate to say that this object is composite because, not because, if one situation where it's legitimate is that these constituents are only mildly off-shell as compared to their counterparts, asymptotic counterparts. Okay. So in other words, this is true about molecules. In other words, to knock out the molecule out of the table, okay, the momentum transfer that I need in a process is much milder than the mass of a molecule. Okay. So in other words, that's why molecules, they continue to have some identity even within a table. Okay. That's why you say, okay, molecules consist. I can think in terms of this guy as a composite. Okay. This is one thing, one property that the ordinary bodies satisfy. What is the other property? The other property is that you can have, essentially this is what I just said, you can have processes with momentum transfer, okay, which is smaller, which is smaller than some characteristic energy by which you characterize your constituent, okay, asymptotic state. Now, these three conditions, if they are satisfied, okay, then it's convenient to call an object being composite. Okay. Now, however, at this point you should stop me and tell me, no, but this is too restrictive. Okay, to impose these conditions. Okay, because we have entities in quantum field theory which we consider composite but do not satisfy these properties. Okay. For example, let's take baryon in QCD. Baryon in QCD doesn't satisfy these properties because quarks are not asymptotic states. Okay. So, for example, okay, quarks do not exist. Okay, so baryon is a bound state of quarks. I don't know, sometimes people visualize this in this way. Okay, and quark bound state if I have QCD and SU and QCD. Okay, the quarks are not asymptotic states. Therefore, all these things, these comparisons, I cannot make. Despite the fact, nevertheless, it's useful to think about baryon as a composite. And because of very special property of asymptotic freedom, okay? Because of this very special property that there is a region of length scales on which description in terms of quarks is the right description. That's why we say that baryon is composite, okay? Not because of this property. Okay, so now what I will try to do first, I'll try to see if, so in other words, I don't know, you can call this as a requirement, weak requirement of compositeness or strong requirement, whatever you want. So, yeah. Because the Compton wavelength is much smaller than the geometric size. Yeah, but sure, no, that's perfectly fine, but then you should define geometric size. What do you mean? Yeah, I mean, okay, this is true. What you are saying is true in fact. For example, we can do this type of exercise with elementary particles. Okay. Now, with elementary particles, we can produce something which has arbitrarily low energy. If I have massless elementary particles, I can produce something which has arbitrarily low energy. Okay. But arbitrarily long characteristic wavelengths. Okay. For example, I can create a coherent state. Okay, of with extremely low energy photons. It could be arbitrarily big. Right? Yeah, you can say, but I mean this this property that what you just mentioned from here will follow automatically. Okay, but you want to what you are saying, if I understood correctly, what you are saying is that you want to substitute instead use that one. Yeah, okay, but I mean for me this is a little bit more well defined. Okay, so but yeah, but you're right. That property is there. Yes. Any other questions? Okay, so then, so what I will try to see if the black holes are have some sort of constituency in this sense. Okay. All right. Then. Okay, so now let me. So therefore, the question that I'm asking is the following: suppose I have a black hole of some characteristic, which in classical description has certain characteristic geometric size r. Okay, wavelength, the gravitational radius r. So this would be the size, for example, corresponding to this question, and ask this question. Okay. Is this an entity? Should I treat it as an elementary on this scale? By the way, one thing I want to mention is the following thing: that whenever whenever I ask this question of compositeness, okay, there is no absolute meaning to compositeness. Always there is a question about the length scale. When I say that something is composite, I'm asking at what length scale it is composite. Okay. And this a priori is not related necessarily with the mass. For example, let's take this example from QCD, right? In QCD we have pions, okay? Now pions are, these are quark anti-quark bound states, right? I mean, crudely, they are quark anti-quark bound states, but at the same time they are Goldstone bosons. So if quarks were exactly massless, okay, as you know very well, pions would be massless. So pions would be Goldstone bosons. Nevertheless, they would be quark anti-quark bound states in some sense. Okay. Now with a massless pion, I can form even a classical object by superimposing many massless pions on top of each other. Okay, multi-pion state. I can create a pion wave, which is in very good approximation classical. Okay. Now that pion wave will have one type of compositeness because it's simply made out of many pions. Okay. Whereas pion itself has another type of compositeness at the QCD scale. So you see, there is a hierarchy of scales. Okay, so in other words, I can create a coherent pion wave of the wavelength, certain wavelength L, much larger than the QCD length. Okay, QCD inverse. This is approximately 10 to the minus 14 centimeters. Okay, let's say I can produce a pion wave of 1 kilometer wavelength. The pion, there's no problem. Okay. I'm working with massless quarks. And of course, this wave will be composite in sense of pions, because it will be composite of pions. But pion itself is composite at the QCD scale of quarks. Okay, so there is a hierarchy. So the length scale is important. So therefore, what I'm asking is the following. I have a black hole of size, gravitational size Rg, so multi-classical size. Let's take black hole in the center of our galaxy. Okay. And let's ask this question. On that